So today marks the beginning of a series of applications of what you've learned so far. So in this class to date, I've taught you most of the building blocks that you're going to need to solve any of these problems. And now we're going to look at very special loading cases. Right, so we've talked generally about the stress state acting on an element, how it can have those 9 unique stress components. Each of these types of geometries and loadings are going to correspond to certain combinations of those 9 components, where many of them will be 0 and then others will have a non-zero value. And so I want you to always keep in mind that there's a bigger picture, there's a more general concept, and that's what we've already talked about, is that we could have any 9 stress components acting on a material element and we know what to do with it. Whereas this is just giving us very distinct cases that are common in our experience as engineers. And so the first one is what we call uniaxial loading. Does anybody know what uniaxial loading is or can remind the class? Right, we're going to load the material along the axis of the specimen, and in particular in just one direction. Okay. So when we do that, it might look something like this. So here we have a material that is, say, fixed at the base. Might say this down here is fixed. And we have a force pulling up on this member. And the very first concept that I want to tell you about when we start talking about these different load cases, and in particular axial load, but this really, St. Venant's principle really transcends all the load cases. It's the idea that when you apply a load, if you are looking at the stress state far enough away from that load, it will take on a uniform stress state. Or, okay, let me rephrase. So St. Venant's principle tells us that if we look far enough away from the point of application, any stress state that we look at will have, as long as it has the same sum of forces, it will be representative of that loading. So right at the point where you have the loading, your stress state is going to vary widely. You can see here, because that load is applied at just one point, it's significantly higher stress in the middle as opposed to the sides. And then as you go a little bit farther away, it kind of becomes more like a uniform stress state. And so the point that I'm trying to make is that if we have a different type of loading, so for example, we could apply the same magnitude of loading but in 2 different locations, if you look far enough away from that point of application, it no longer matters which way you applied the load. Because if you go far enough away, the same thing will happen. You're going to end up with this more or less uniform stress state. So if you want to know the stress state right up around the load application, that's a much more complex question. And typically we solve for that using some type of software where we model it and we do a finite element analysis and we check and see how the stress distribution changes throughout the cross-section. But if we're designing far enough away from that, then it doesn't really matter how we say the load is applied. We can apply it in the easiest way for us, because it's going to end up being more or less this uniform stress state or some type of predictable stress state that as long as we can, as long as we have the same moment and same sum of forces, we'll have the same stress state acting on the object. Okay. So we're going to talk a lot about average stress when we do normal stresses, or when we do uniaxial applied loads, we're going to calculate P over A. But I want you to always keep in mind that that's because we're dealing with kind of the central region of this body. We're assuming that we're far enough away from the load application. But if you want to know the exact stress in that load application area, that's a more sophisticated question than we cover in this class. And really that's a more important question. Why is that a more important question? Where is this object going to fail? Where the stress is greatest. And if we have a uniform stress state kind of in the middle, and we have the same force having to transfer through the entire object, if we have this non-uniform stress state, but it sums to the same force, this magnitude must be larger than the average, correct? This maximum value. So really what we're doing in this class is very simplistic because it doesn't really tell us where the object's going to break, but it's the tool that you have now, and you'll get more sophisticated tools as you continue your education. All right, so if we apply a loading, we know that it must be in equilibrium with the internal forces. So because of St. Venant's principle, we could say it doesn't really matter how we've applied this load. In the middle region, we're going to assume that we have P over A. We're going to assume we have some average value of stress, and that all other stress components are going to equal 0 because we don't have any forces acting in that other direction, so therefore we say we probably won't have any stresses. So I'm assuming this stress state, and then I'm going to show that it satisfies equilibrium. And if it satisfies equilibrium, it's a plausible answer to what the stresses could be. So I can show that one of two ways. I can do that looking kind of at the member level. So I can verify the equilibrium of the cut member. If I cut through a cross-section and I integrate the stress acting on that cross-sectional area, I'm integrating the magnitude, the stress magnitude is P over A. So I'm integrating P over A with respect to the area, and that equals P. So essentially what I'm saying is if I assume that this is my stress state, if I assume that P over A is my stress state, and I take a cut here in the middle, and I integrate that assumed stress over that cross-sectional area, I get that this force on this plane is P, which puts it in equilibrium with the applied force P, and therefore that's a plausible stress state. I can do the same thing at more of an element level, so a material element. I can say that any material element in this member has to be in equilibrium. Excuse me. And so I can take the partial derivatives of the normal stress. I'm assuming this is an x direction, this horizontal direction. So I can take the normal stress in the horizontal direction with respect to that x variable. I can add that to the partial derivative of the shear stress, but the shear stress is 0 throughout, right? So that means this term is 0 throughout. I also don't have a body force applied here. This is kind of simplistic because everything that we deal with in reality does have a body force, gravity, if not some other force. But we haven't said anything about gravity. So we just have the one component. What's the partial derivative of P over A with respect to x? 0. P over A is a constant. So this whole thing equals 0, therefore I'm in equilibrium. All right. So let's say, I don't know about you, but I prefer for gravity to always be up and down, even though there's no particular reason for that to be true on this slide. I like for it to be up and down. So if I have the same member up and down, and I apply P, now the stress is still going to be P over A, right? But my question is, now let's say that gravity exists. So if gravity exists, we now have this f of x, this fx. So how do I figure this out? What's going on? Because the partial derivative of P over A is 0, but if I have an fx, which is my gravity force, this no longer equals 0. So am I violating equilibrium now? Is this no longer the solution?
I think it depends on direction of the force application. If you subtract off, then you should sort of cancel out gravity.
The force is being pulled on both ends. So it's being pulled up and pulled down. And gravity is also acting downward. So we've got gravity here. Yes.
Because gravity is so insignificant, it doesn't affect the equation that much, that's disregarded.
I would say that entirely depends on the weight of this object. In most cases, I would say yes. So if you're applying, thousands of pounds of force on a very small object, then the weight of that object is going to be very small in comparison to the applied force. Yes, that's a very true statement. And that's probably why we ignore it in all of these calculations. So from a practical perspective, that's a true statement. But what if I don't want to be practical? What if I want to be very technical and I want to account for every little force? Not necessarily subtraction, but maybe an addition. So I think what you're they're kind of superimposing, yeah? Okay, so think about how gravity acts. If I am looking at this point here at the bottom, how much force is pulling down on that point due to gravity? How much of the bar is below that point? 0. So there's no force pulling down on it as a result of gravity. What if I look at this point at the top? Now how much force do I have? So you have the whole weight. So you have the volume times the density or the mass per unit volume. So you have the whole mass or the whole weight acting down. And if I were to go any point in between, I'd get some linear value. It's going from 0 to the maximum weight. Would you agree? Okay, so in reality, what's happening is you don't have a constant stress state. Due to that loading, you have a constant P over A throughout, but then you have that small effect of gravity that grows as you go up the object. So you've got a little bit at the top, you have the whole weight pulling down on it. At the bottom, you have none, and everywhere in between, it's dependent on its location, it's linearly increasing. And so the point is, this term here then becomes a linear function of x. So you take the derivative and you get a constant that's going to knock out this fx term. It's not something you need to spend a lot of time worrying about, but I just want you to keep in mind what's really happening. Okay, so the thing that you really need to take away is that when we have uniaxial loading, we can presume that that results in a more or less uniform stress state P over A, as long as we're far enough away from the point where we apply the load. And that's something that I forgot to mention. So if we have dimensions here, let's call this T, W, and L. So we have T, W, and L. And when I say far enough away, we quantify that as being at least the largest dimension of the loaded cross-section. So the loaded cross-section is going to be this cross-section here, because that's where the normal stress is acting. And the largest dimension of that is W. So that's saying that you need to be at least W away from that end of where that point where the load is applied in order for you to get this more or less normal or uniform stress state. Okay.
Sorry, can you explain how we dealt with the body force again for the vertical member. You sit there.
Here? Yeah, so the body force is some constant value, this Fx value. And the normal stress is your P over A plus some function of X, a linear function of X that goes from 0 at the bottom to the full value of the weight at the top. And then when you take the partial derivative of that, you end up with a value that is equal to your Fx force. And so then, well, it's going to be negative of it. So they're going to negate each other. All right, so you're not going to turn this in, but I do want you to attempt this before I show it to you. So go ahead and draw the Mohr circle for the uniaxial stress state. So uniaxial stress means we have this one normal stress and no other stresses acting on the material. All right. Go ahead. Yeah, those are good. So he's giving us a point that is at sigma x and 0, and sigma y and 0, where sigma y is clearly equal to 0. There we go. There we go. Yeah, we'll imagine that looks more circular. Okay, so awesome. So what I want you to see is that when we have normal stress, the Mohr circle is always going to pass through the 0, 0, and then it's going to pass through whatever that applied stress is. And it could, in this case, we have tension, so it's in the positive region. If we had compression, it'd be on the other side, the negative region. Okay, so question for you. What would the other two circles look like? Because remember, there's actually 3 circles. We can rotate this object around 3 different axes. There won't be a circle for one? Is that what you said? Yes. So Chidozi makes a really good point. One of these circles is really just a point at 0, 0. Because we know that the other 2 circles are going to pass through 0, and they're going to pass through one of our in-plane principal stresses. So if our in-plane principal stresses are 0 and sigma x, and then our third principal stress has to also be 0, we're going to have one circle whose principal stresses are 0 and 0, which means it's collapsed into a point. And you can see that if you were to rotate this about the x-axis, we're then looking at this side, that side, the back side, those 4 sides. Okay, you see what I'm doing, going around like that? And so we're rotating it about the x-axis. None of those sides will ever develop stresses because there are no stress components in any of those directions. Okay. And then the other circle will have to pass through 0 and sigma x. But now this is a different 0. This is not the 0, this is the in-plane stress, it's the out-of-plane 0. But for all intents and purposes, it's the same circle as we had before. So what does this mean in terms of our absolute maximum shear stress? Will it be in plane or out of plane? It will occur in plane, but it's a trick question. It will also occur out of plane because we have 2 identical circles. But we can figure it out just based on our in-plane values. It's going to be this maximum shear stress here. This is going to be our radius, which is our maximum shear stress, which is equal to what? What's that? Not P, it's sigma over 2. Because the average of 0 and sigma x is half of sigma x. So uniaxial stress is simply the case in which this is what our stress state looks like. Okay. Stress concentrations. So I told you that the average stress is useful. It's more or less easy to calculate, but it's not necessarily what we designed for, because the object's not going to fail at that average stress unless the whole object is experiencing that average stress. If there's any concentration of stress anywhere in this material, that's where it's going to fail. It's wherever it gets the highest stress. One of these tools, which is helpful, is being able to calculate stress concentrations. So I told you that to get the stress distribution at that end, you would need to do, like, say, some finite element modeling. Well, there are certain geometries that people have studied and then created equations to where, without knowing the whole stress distribution, we can get what the maximum stress value is for that geometry. So for example, if we have a plate with a circle in it, and we apply loading at the end, excuse me, then the distribution of this load is going to look something like this. So it's no longer a uniform stress, but instead it's increasing as we get closer to that discontinuity in the geometry. And we can kind of look at the inverse of that. Okay, so we might have like a dog bone shape. Not like the dog bone you feed your dog, but what we call in structural engineering is a dog bone, where we have a thicker section that then comes into a thinner section. And if we do that, then similarly, the stress is highest as you approach those regions where the cross-section is changing. So as you approach those corners, then you're going to get a higher stress. So these values here are our maximum and our maximum, and that's what we want to be designing for as opposed to the average. And so the way that we do this is through what we call a stress concentration factor. Okay. And that's equal to the maximum stress over the average stress. So you can calculate the average stress by taking your force dividing by the cross-sectional area. You can get your stress intensity factor, say from a table, where you match up your geometry with the values of the table. You get your stress concentration factor. You then multiply that by your average stress, and that will tell you the maximum stress that you're designing for. So one of the most famous stress concentration values is a hole in an infinite plate. So, and it doesn't necessarily have to be infinite, it just has to be so large or so wide that that dimension is very large relative to this circle. And now your stress concentrations are going to be at these two corners here, and that value is equal to 3. So the stress right at the edges of those circles is 3 times the average stress that goes around the circle. So 3 times the stress acting that you would expect to be acting as an average value on the sides of the circle. Now the magnitude, excuse me, the magnitude of K is affected by a couple things. So there's a radius that goes along with this circle, R, and as that radius gets smaller, I don't know why this pen keeps stopping. The K value gets bigger. So as you get a smaller and smaller circle, or the radius of that circle gets smaller, your stress intensity, or sorry, your stress concentration factor gets larger. And the other thing is, and that applies here as well. You have a radius here. Okay, you also have the ratio of D over D, where big D is the outside dimension and little d is the inside dimension. And as that goes up, that means that you're cutting in more to this member, so you're making the small section much smaller relative to the outside section. So as that goes up, your stress intensity, sorry, I keep saying the wrong one, your stress concentration factor also goes up. Yes, K goes up. Yeah. So you can think of it as like this force that starts out more or less uniform has to get kind of channeled in here. And so it's got to kind of all get in there. So the smaller you're making that middle section relative to the outside section, the more that force is having to really squish together. And that means that right here in these parts where it's coming around the bend, they're seeing more stress. Because when the radius goes down, it's starting to act more, let's see, it should be starting to act more like a sharp crack. Does that make sense? So if we go, like the extreme case would be something like that, where this is a 90-degree corner. And so that has the worst stress concentration as opposed to rounding it out. So let's see. If this were a really big radius, it might have a connection like that. And then if I make that radius smaller, it starts going like this and like that, and it approaches that corner. It's a little bit harder to conceptualize when you're thinking of a circle. But the idea is that the smaller that radius, the more it's acting like a square corner, or even worse than that, like a crack. So the worst case for this would be if you have just a slit here, where if you zoom in on this, you know, you could have like a radius of this corner, and as that radius gets smaller and smaller, it becomes essentially just a sharp crack, and that's the worst case. for that type of opening. Do you have a question?
I was going to say, what happens when R becomes 0? This case going up.
Yeah, then you'd have really high stress concentrations. And that's what this sharp crack is. Essentially this, when the radius becomes 0, the stress becomes infinite. And then you can no longer use anything you know for mechanics and materials, and you have to turn to fracture mechanics. All right, so I want to show you how we calculate deformation in axially loaded members. And I want you to see that it is entirely things you already know. Okay, but I want you to be able to get back to this equation if you had to, using the basics. So what I mean by that is you should have ingrained in your mind this stress and strain relationship for normal stress and normal strain. Okay, so we say P over A for our stress, and we say the strain is elongation divided by initial length. And we've already talked about material relations for normal stress. We have the 3 different strains, and they're a function of the 3 different stresses. So that's the general case. And now we're dealing with uniaxial stress, so we know that 2 of these stresses are 0. So whichever direction this is, in this case, we're choosing this to be the x direction. We're saying sigma x exists, but sigma y is equal to 0, sigma z is equal to 0. So we'll say sigma x is not equal to 0, but the other 2 are. So we plug that in to these equations for the material relations. And we can get our strains that way. So the other thing we look at is the axial deformation. So how much did it actually extend? Not just the strain, but the elongation. So if we take the strain in the x direction, because that's the way that it's elongating, and you're going to have the transverse strains in the other 2 directions, and you may be interested in those, and you can do the same thing with those, but the more interesting information is the longitudinal direction, because that's where we're seeing most of the displacement. So strain, we plug in deformation over length, so that goes on this left-hand side of the equation. On the right-hand side of the equation, that went there. We're going to plug in that the stress in the x direction is P over A. So that goes here and comes over here. And then these other 2 are 0. So the other 2 stresses are 0. That goes here and there. Oh, wow, that's not easy to see. And then you may or may not have a temperature effect as well, and so that gets tagged on to the end. So now if we're solving for the elongation, we need to multiply both sides of the equation by the length, and therefore you end up with the elongation equal to PL over AE plus the strain due to temperature. So I'd say this is strain due to temperature multiplied by the length. That gives you a deformation as opposed to a strain. So this equation is what you're going to want to use. And if you'd like to memorize it, you can. But what I'd really prefer is that you know these things on the left-hand side that we've been talking about for the last month, and that you then are always able to get this equation for deformation because you know that you can just plug in the values of normal, or the equations for normal stress and normal strain into this material relations equation, and it will give you this. So this equation here on the right is simply the material relations equation when you plug in the values that correspond to uniaxial stress. So when you plug in the strain and the stress values that correspond to uniaxial stress. And sometimes we refer to it as the force deformation relation. It's really the same as the stress strain. We've just multiplied by length on both sides so that we get deformation. You can do the same thing for the transverse direction. Both of the transverse directions are going to have the same strain right here. And if you'd like to turn that into an elongation equation, multiply both sides by the initial dimension in that direction. So you don't multiply them by L, you're going to multiply them by, say, the width or the thickness of the member. Any questions? Okay, so we can use this force deformation equation to calculate the amount of elongation of a member, but sometimes the member is broken up into different components or different segments. So you might have, say, one segment that looks like that and another segment that looks like this. These could be two different cross sections like I've shown here, or they could be two different materials. And in that case, they no longer have either the same A or E, or possibly both. If they're different cross sections and different materials, then both A and E are different. And so what that means is you need to treat each segment as its own, say, element, and then add them together. So for segmented bars, you do the force deformation equation for each segment and figure out the elongation of that segment. And then it's the sum of those elongations that gives you the total elongation. And then if, for example, you have a cross-section that is changing over the length, but there aren't any sudden changes, instead it's maybe controlled by a function. So you might have a member that starts out with a certain, so say it's kind of like a, you know, like the cones that you put out when you don't want someone, like safety cones. They start out with a certain kind of small radius, maybe 2-inch diameter, and then they have a bigger radius at the bottom. Everybody knows what a safety cone is? Okay, so if we were to apply load to that, that area is changing, but it's a linear function. It changes with the height of that cone in a linear fashion, or the diameter does. The area is probably actually maybe squared. But the point is you can get that function. So you can get the area as a function of x. In the most general sense, you can get E as a function of x, but that's a little bit strange. I mean, more than likely it's going to be a constant E value. But A certainly could be a function of x, and then you could integrate this force. And also the force could be changing, because remember we said with gravity especially, that force may not be the same throughout, so you could be integrating both the force and the area over the length. There are two major types of configurations for axially loaded members. One is placing them in parallel and applying a load P to those two parallel members, and the other is series. So when I said that you calculate the displacements of each segment and then you add them together, I was referring here to this series situation. In series, we know that the force in each segment is equal, Because if you were to take a section cut at any point in either of those two segments, you would find that the force has to be P. Would you agree? The internal force has to be P at any point in there. Now, I want you to be very careful, though, because equilibrium tells us that the force is staying constant throughout, but the stress is not necessarily staying constant. The stress is the force over the area. So if the cross-section changes, the stress will change. So you have your two forces equal to each other, and your elongations sum to equal the total elongation when it's in series. Let's see, this is series. And your force deformation equation doesn't change regardless of which situation you're in. You have the equation that we derived before, where for any segment, so this would be, segment 1 and segment 2. For each of those segments, they each behave according to this material relation equation. Same thing in the parallel. For the rod on top and the rod on bottom, each of them independently has to abide by this relationship between the force being applied and the deformation that's occurring. But now when we're dealing with parallel, the thing that's a little bit different is that the force is no longer equal in the two, but instead it has to add up to the total. So if you were to take a section cut, you would have two different forces which have to add up to P. In certain cases, they will be equal. So for example, if these are the same material and the same cross-section, and they're symmetric about the force, that's a special case in which you'll have equal forces in them. But they may not be the same material, they may not be the same cross-section, they may not be symmetric. There's a lot of things that could change that would make it so that they're not the same force in them. The second thing is the compatibility, the way in which they interact. If you pull on this, and you pull on it such that the right-hand edge stays vertical, then they both have the same elongation. Do you see that? They both have to stretch the same amount for that to happen. But sometimes what happens is you pull on it, and this plane becomes inclined because maybe one of those members is more rigid than the other, and it's harder to pull. And so unless you have a moment forcing it to stay vertical, the tendency is for the less rigid member to want to elongate more than the other. So now what you have is this displacement. Well, let's see, it probably really goes to there. That displacement and that displacement. So now they're not equal, but you can get a trigonomic relationship between the two. Because you can maybe know this angle here, how much that plate is rotated, and therefore you know that they have to be related to each other.